All right, it's 5 p.m. now. I'm gonna get started. If I could get y'all's attention. If you don't know me already, I'm Eddie. I was here for the last midterm review session. I hope that was okay. I'm trying something a little different for this one, so it's not so boring. Um, this is just like a clone of Kahoot, because Kahoot costs money. So this is quizzes. We're doing a quizzes today. If you guys haven't joined already, go ahead and join. The winner of this will be getting $10 Target gift card. So be sure to lock in. You might need like a pencil and paper to work out some of the problems. So have that ready. Um, Again, as always, I haven't seen the midterm. I have no idea what it looks like. So I tried to cover a little bit of everything with this. I literally went through the slides starting from where midterm one ended and then went up to lecture 17 and tried to include all the main stuff. Um, this is going to be recorded. It'll be posted to Canvas. And also, all these quiz questions will be posted on Canvas sometime today after this. So if you guys want to play with your friends, feel free. All the questions will be there. Um, so for everyone who just joined, we're doing a quiz is today, so you can just join in through the code. Is everyone in right now? Anyone not in? Okay, cool. I'll give you all a quick second. And we might not get through all the questions because there's quite a bit, but again, these will all be posted. Um, so you can take a look at them yourself. I think we should be able to get through most of them, hopefully. I don't know. All right, anyone not in? I know you just came in. Okay, cool. No worries, no worries. And again, the prizes. You know what? I'm gonna stick it right here, just so you guys are reminded what the prize is. You know, it'll keep you guys motivated. You know what I'm saying? I don't know. Welcome. All right. I'm gonna go ahead and start it. Um, oh, okay. I'm just gonna go ahead and start it. Um, yeah. So this will be in like sequential order from like the stuff you guys learned from the end of midterm one to what you guys recently learned about like heaps and stuff. So here you go. I might have not made enough time for you guys. I'm not gonna lie. Okay, if you can answer it, you can answer it. Time is the name of the game. Okay. Um. Cool. Yeah, we mainly got it right. I'll go over all the questions. And show why the ones are right. All right. So we're asked all the all of the answers which describe abstraction. So this first one is like kind of like a real world anecdote. You know, like when you drive a car, you don't need to know the inner workings of the car or how all the moving parts work to drive it. You only need to know, how to like steer, how to accelerate, how to shift gears, just like the stuff that the car company provides to you. That's a real world example of abstraction. It makes it so that not everyone has to be an expert on cars to use cars. And that's a very big part of software and programming. Not everyone needs to know the inner workings of your software or framework in order to use it. Here's a more programming specific one, creating a string in Java. So Okay, a string is just a data type, but as we know, a string is like an elevated class data type that Java provides. And you can do things like, I don't know, you can get things like the length of the string, and you get access to all these methods like to uppercase or to lowercase and all that. And those are all methods which you can just, once you create the string, you can just go ahead and plug it in and use it, right? You don't have to rewrite the to uppercase, to lowercase length, all those methods again. So the string class is provided by Java so that you can simply create a string and do all the things you need for it. Um, so that's an example of abstraction. And finally, using Windows to utilize a computer to surf the web. Um, Again, this goes with the same idea. You don't need to know all of like the inner workings of your computer, all of the parts, how the electricity flows through the computer. Once you download Windows or an operating system, that abstracts all of that away from you, right? So all you got to be concerned about is how to operate Windows itself and not how to operate the inner workings of your computer. But anyway, yeah, the general idea is that abstraction hides away the inner details and makes it easier for an end user to just um, directly access everything they need to access. I'm gonna give you guys more time. This is like way too little time. That is my bad. I'm just gonna. I may have underestimated how long it takes. I'm just gonna give it all 1 minute time limit, or you know what, 45-second time limit. Let's just do a healthy compromise. Okay, that is my fault. That is very unfair to solve. All right, so if you guys could join real quick, we can get this started again. And if you guys have questions at all throughout these questions, just go ahead and raise your hand, and I'll be happy to answer. Anyone not in? Oh, oh okay. I think we're good. All right, I'm starting it. Can I skip this? There we go. All right, here we go. So, I have no idea. I'd imagine we'd have like one, maybe, but take that with a grain of salt. I haven't seen it. Yeah, so I guess there will. Okay. All right, good job, Jack. Let's go. Um, so this question is about encapsulation. There was multiple correct answers. If you guys didn't remember, encapsulation is the idea of, specifically to Java, when you create a class, you want the information about that class to be kind of like local to that class and only accessible by the class and not like freely accessible by everything. Um, because that's just not a good practice. And again, in a future question, we'll explore that more. But looking at this first one, we see immediately here, when we define the dog class, we created a public string name and public int age. basically we're exposing the inner contents of the class to whatever part of the program wants to alter it. Here we alter right here. That is not an example of encapsulation. Encapsulation, just rule of thumb, think of it, you're making those inner variables private. So they're only accessible by the class itself. They're encapsulated within the class. So see here, we created private name and private age. They're not accessible directly. In this implementation, we make them accessible by these methods we create, set age and get name, set name and get age. Here, this would be a good example of encapsulation because those inner variables are private and we're only allowing access through our own terms to the class. And here, same idea, they're private. This time, instead of using like the setters, we just set them directly in the constructor. Again, same thing. Main part of it is that those inner variables, they're private and they're only local to the class. So just keep that in mind. All right, next question. All right, so this question was about why we're using these getters and setters, or more specifically, why we're using encapsulation. Because remember, when we encapsulate our variables, we make them private. So the only way to expose them to the other parts of the program were to have those like get age, get set age, get name, set name, methods, right? So the reason we're doing this is because consider this example. We have a dog object, right? And someone tries to set the age to like a negative age. If we just had the variables public, right? There's nothing stopping them from doing that, which is not good, right? Because a negative age is impossible. So the reason why we want to create these getters and setters is we want the user to access our information on our own terms. That way, in our setter method, we could say like, if the age is less than 0, then we're going to throw an error or we're going to do something else, right? So that lets us control that unexpected behavior and make sure that everything is going up to plan and making sure everything is going as expected for our class. So the correct answer here would be this last one. All right, so this is just a quick question about interfaces. This was mentioned in the slides. If you don't already know, an interface is kind of like the blueprint for a class. So if a class implements, say our class human implements organism, we're essentially like saying that, okay, since human implements organism, it's guaranteed to contain these methods which define what an organism does, right? So the correct answers here are get age, set age, and move. And let me explain why you don't have to necessarily implement eat and age. Well, if you notice here, for this eat method, it's different from the other ones in that it has this default keyword in this implementation. Oh, I forgot a semicolon. Um, anyway, what this default implementation does is that it's saying that if whoever's class that is implementing this organism interface, if they fail to override and implement that eat method, the interface is just going to go ahead and provide code that'll just do stuff by default if nothing else is provided. Um, Otherwise, the user could override it and make it do something different. But in this case, the human class doesn't necessarily have to override eat because eat already has code associated with it by default. So that would run without error. And finally, this age, this is kind of a trick question because I had these methods get age and set age, like heavily implies that we should include an age variable, which we probably should. But Java, like Java itself, because it's not directly stated in the interface that this age variable should exist. This is more so an implied thing rather than something enforced by Java. So if you didn't include a variable called age, the class would still work fine without crashing. This question is case sensitive, by the way, so be careful. All right, good job, Juan. Um, yeah, so the correct answer is at override. Essentially, when you're implementing an interface, anytime you want to like actually write code for any of the interface methods, for example, we had eat, get age, set age for that last organism interface. Before you actually create the method in your class and write code for it, before that, you got to put it at override. It's telling Java, hey, instead of this interface code, use this class like explicitly defined code instead. So make sure you guys keep that in mind. Might be a little tricky. So this was a question about generics. It seems like most of you got it. So I'll just go over this quickly. The specification of this class says that we want anything to be in the simulation so long as this thing is comparable with each other. So that should immediately click in your mind that this is involving generics because generics allow you to use whatever data type is specified by whatever end user is using this class. Um, And in the case that we want this specific thing, so again, it can be anything, but we want it to have guaranteed some certain functionality in that it needs to be compared. So here, this is the correct answer, by the way. We define the generic, but the generic, we have to make sure that these things, these T things, are comparable with each other. So we're ensuring that T implements the comparable interface such that this data type must be comparable with others of the same data type. But other than that, it can be anything you want. So this is just to show that generics, you can still put constraints on them, but they're still generalizable to whatever you want for the class. All right. So if you guys think about it, like a doubly linked list, um, it's going to have the same average time complexity as a singly linked list. To those of you who said true, I think you might be thinking of like a doubly linked list might have access to a binary search or something like that, I'd imagine. But if you're searching through an element in a linked list, whether it's doubly linked or singly linked, you can't just like jump to the middle, right? No matter what, unless you already have the pointer on hand, which in this case, you assume that you don't. But you can't directly jump to the middle. The only way to get to the middle in any linked list, whether it's singly or doubly linked, is to start at the beginning and work your way up until you're at the middle. So even if you did try to use a binary search, just getting to the middle, that's going to take n divided by 2 operations, right? Because you're jumping n divided by 2 elements to get to the center. That's already like an O of n operation. And we already know that a singly linked list is already still O of n because you have to directly search. So no matter whether it's singly or doubly linked, your best option is just to do a linear search through the linked list. So it's going to have the same average time complexity. Just keep that in mind. All right. So this is just kind of like going over an example of why doubly linked lists can sometimes be good. Like we said, the search wasn't any better. So what's the point of this? I'm going to whip out my iPad for this. Let me screen share. Okay, so it's saying if we have some linked list, I'll just draw it like a really quick, crude example. Sorry for my handwriting. All right, say we want to delete this middle node here. So again, for deletion, typically the time complexity is assuming that you're already at the element you want to delete. So we don't have to factor in the search. So let's just say like we have information about this node right here. We have a pointer to this node. All right. So if we have information about this node, let's think about the singly linked list case. Here, you know what? Let's just say there was like a bunch of elements before this one, right? So there's a bunch of elements beforehand, and then there's one we had to delete. So in the singly linked list case, all we have access to is a pointer to the node we want to delete, right? Right here. How are we supposed to get the one beforehand? Well, the only way to do that is, again, linked list. You're going to have to start at the beginning, and you're literally going to have to iterate node by node until you get to the one that was right before the node we're looking at. And that right there is an O of n operation, which instantly makes the deletion for a singly linked list O of n, which is not good. So here's why doubly linked lists are good. Here's like a particular reason why. If we had all these doubly linked, instead of having to go to the beginning for the node beforehand to kind of like, as you know, if you want to delete a node, you go to the one beforehand, you switch the pointer to the next one. Since we're already doubly linked and we have a pointer to this node right here, all we got to do is just go back to this previous pointer, and then we now instantly have access to the node beforehand. And then boom, all you got to do is just do the whole thing where you switch up the pointers, and then you deleted the node. So in a nutshell, that's why it's so nice. It's because if you want to delete something, all you got to do is just go to the one beforehand directly and delete it. That's an O of 1 operation as opposed to O of n. All right, seems like most of us got it. Again, should be pretty self-explanatory. Um, I'll just quickly do it on my iPad in case you didn't know how to do this one. Oh shit, I forgot the numbers. Okay, I hope you know how to do this one. I'm just gonna move on. It looks like most of us got it. Okay, so we're asked the best case time complexity of searching a BST. Um, as you guys know, when you're searching a BST, here I'll whip out the iPad. If you search through a BST, oh, if you search through a BST, you have to start from the top and work your way down. For example, I don't know if we had a BST where it's like 12, and then something, 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 arbitrary tree. You have to start from the top, and then like if the thing you're searching for is less than 12, then you go to the left. If it's greater than 12, you go to the right, and all that. The best case is that if you're searching for 12 itself, and since 12 is exactly the root node, as soon as you start searching, you found what you were looking for. So no matter how many elements were down here below the root node, like the size of the tree, it doesn't matter because you immediately find 12, right? So in the case that what you're searching for is directly the root node, since you start searching the tree, you're going to directly find it on the first step. So that's always going to be O of 1, no matter the size, for the best case. Okay, I might have. This probably was an issue. I probably should have made this like a fill in the response, but it was O of H. Um, again, that's my fault. Sorry about that. But yeah, the correct answer is O of H, no matter what the BST is, where H is the height of the tree. If you said O of N, that's not correct because um, if it was O of N, then it would be no better than like a unsorted array or a linked list. Um, I'll show a concrete example, I guess, make it more sense. Make it make more sense. Uh, right. So if we're like, again, we had an arbitrary BST. I don't know. It looked like this. Um, the worst case would be, as you'd assume, if one of the elements we're trying to search is here at the bottom, right? Because if we're starting from the top, so we're starting from this node, and every step we can either go left or right, aka down one layer. So maybe like the next step we go left, and then now we're down here, and the next step we're down here. The most possible operations you can have is if you go down as much as possible, aka you go down um, h times, which is the height of the tree, to get to the bottom. So yeah, it'd just be O of H for this one. And again, the average time complexity, you'd expect it. The reason why it's still O of H is because, I don't know, you expect something to be in the middle. That's 1/2 H. You just drop the constant term, and that's still O of H. So there you go. Yep, it'd be log n. So, as you guys might have saw in the slides, only when the BST is balanced, H directly will approximately equal log n. This is because when it's balanced, like the tree is arranged in such a way such that like there's no one side or one layer that has like significantly more elements. So if we assume a certain structure which is balanced, then we automatically know the height is approximately going to be log n. But again, the key word here is balanced, and you'll see another question about this. Keyword here is balanced. Don't always generalize that O of H is exactly log n. You'll see here in a second. I might spoil it. Yep, it's false. So here's why. So earlier we said no matter what the BST is, the worst case time complexity for a search is always going to be O of H, right? Because you're starting at the top. Each step you go down one layer. You can go down at most H layers. That's worst time complexity O of H. Because this is a balanced BST, we already can assume that H will exactly equal log n. Again, only because it's balanced. And because the height is log n, we immediately know that the worst case time complexity for a search is O of H, which is equivalent to O of log n. So it would not be O of n. All right, yep, it has worst case time complexity O of n. I'll illustrate why this is the case if you didn't get it right. So again, keyword, make sure you always remember to check if it's imbalanced or balanced because it makes a big difference in what the time complexities are, right? So we said like a balanced BST looks like something like this. You see how nice it is? So that's why we can assume the height is O of log n, right? Because we know it'll follow this general form. It'll look something like that. If it's imbalanced, think of a tree like this, right? This is a perfectly valid binary tree. It's just imbalanced. But we can make it so that the height is directly equal to the amount of nodes because we can just make it go down each step in a direction, right? Even though it doesn't look like a tree, it's still a valid binary tree. It's just really imbalanced. So because in this worst case, for this worst case tree, H will directly equal N, again, because we have N nodes and like they're all contributing 1 to the height. If we're searching for something down here at the bottom, the binary tree, we have to start at the top, and then each step we go down 1, 1, 1. That's going to be O of H, and H equals N. So that's worst case O of N operation. So keep that in mind. Yeah, balanced binary trees and unbalanced binary trees do not necessarily have the same behavior. Okay, so this one, a lot of us got wrong. So yeah, this one might be a little tricky, but I want you guys to think of, to get the intuition from doing your assignment for the BST. Hopefully we all submitted that. So when you're inserting into a BST, the first step is first to search for the parent node where we're then going to place the node we want, right? So okay, so we instantly know that an insertion is going to involve one search. Okay, so we got to search for that element where we want to place the next leaf or the next additional node or whatever. And if you think about it, in all cases when inserting into this BST, like whether there's like two children, it's a leaf or whatever, it's either you just directly insert it or all you got to do is just switch around like 2 or 3 pointers and just insert it, right? Remember, like this assignment is like if there's like 2 children, 1 children, 0 children, no matter what, it just took like a few lines of code to get that new node inserted. It's not like you had to do like some crazy operation to insert it. All you got to do is just switch around the pointers. So what we found is that in insertion, first step is the search, and that which is going to be like O of H in the average case, and then the actual insertion of itself, which is just changing a few pointers in every case, which is just going to be an O of 1. And since that O of H will override that O of 1, because again, O of 1 is overridden by anything bigger than that, it's essentially going to come out that the search and the assertion are basically just going to have the same time complexity. Just because when you're actually inserting the node, all you got to do is just switch around a few pointers once you find it. Does that make sense to everyone? I might have hand waved through that a little too much. But all right, we mainly got this one. Yeah, again, just goes into that point I was driving earlier between balanced and imbalanced BSTs. H is only going to equal log n if and only if the tree is balanced. If it's imbalanced, you can have a tree with height directly equal to n. Remember that example where it just kept going down to the right? And yeah, so that's why it's not necessarily always going to be log n. So definitely be careful with that and always check to see if it's asking for a balanced or an imbalanced BST. All right, this is kind of a trick question. Uh, yeah, this was definitely a trick question. I got you guys good. It's going to be none of these choices, and here's this. This is definitely why for these things you have to consider all possible cases. Um, wait. Oh shoot, I should have definitely put worst case time complexity. Okay. Anyway, sorry about that. Assuming worst case time complexity, um, it's not going to be any of these choices. Wait. Oh no, sorry. I got ahead of myself. Just the time complexity, right? So what it's asking is if no matter the worst, average, or best case, if it's always just O of n, O of 1, O of log n, the natural choice, as a lot of you said, was O of 1, because you might think you could just like, when you delete something, here, let me whip out the iPad again. But yeah, a lot of you guys put O of 1, like whenever you delete something, all you got to do is just switch around some pointers. And then just like shift everything around. What I mean is that like, I don't know, say we had like a BST that looked like this, and say we removed this node, you might think it's O of 1. Well, it would be O of 1 in this particular case, because if you just delete this one, then all you got to do is just like change the pointers around, and that's like really simple to do. Now, the reason why I said it's not going to always be O of 1, and there are cases where this time complexity can change, is remember the case where you have to delete a node with two children. Specifically in this case, here, maybe I'll do it like, maybe I'll do this. Okay, so we have a BST that looks like this. Say we wanted to delete the root node. Now, when we delete the root node, it immediately should be apparent that like there's no simple way to just like, or wait, I guess I'll just put one there. But anyway, yeah, there's no like simple direct way to just kind of like directly move the tree and shift around the pointers in an O of 1 manner to where we can fill the spot where that node, that head node was. And remember, again, this is from the assignment. Whenever you delete this node with two children, you have to kind of find a successor on the left or right. So maybe like you go down and then you go down and you search for something here. That operation to find the next successor, because it could be all the way down the tree. It could either be right next to where you are, like 2 nodes down, or it could be all the way down the tree for your successor. We don't know. It depends on what your tree looks like. But the gist of it is that when you're looking for the successor, that is not an O of 1 operation. It depends on how big your tree is. So for that specific case, that is the reason why whenever you delete from BST, it's not always O of 1. So again, the question, don't be scared by this. This is just kind of a trick question, like to kind of serve as an educational tool. Probably won't get something this crazy on the exam. I just wanted to let you guys know that for these time complexity operations, you might think it's one thing, but then there's just one edge case which makes it another thing. So that's something that got me a lot, and I wanted to share that wisdom with you guys. All right. Did decently good on this one. So this kind of ties into the last question, right? So we already know that like the worst case for deletion is not going to be O of 1. And for the sole reason why it's not always going to be O of 1 is that you have to traverse down and find a successor, right? And in the worst case, if you think about it, the successor could be all the way down at the bottom of the tree when you're removing the root node. So that means you have to start from the top and go to the bottom to find that successor. And as we know, and as we talked about, that is an O of H operation. And this makes sense, right? Because for a balanced BST, the height, again, is going to equal log n. So that worst case complexity for deleting from this balance tree would be log n, which is equivalent to O of H for this balanced BST. And for an unbalanced BST, remember, we said that the worst case height for an imbalanced BST is O of n in the case where you create some kind of tree that just keeps going to the right or one direction, and such that the height of the tree is directly equal to the number of nodes. So in that worst case, if you're like deleting the root node and the successor, you have to go all the way down to the bottom and find it. That's going to be O of H. And since in this worst case, that height is going to directly equal n, that worst case scenario is going to be O of n. All right, we did decently well. I'll use this opportunity to show you guys generally how traversals work in like a really nice way to do it that I've found. Wait, hold on. Before I share my screen, I'm gonna write down the BST so I can actually see it. Give me a second here. 50, 17, 9, 14, 12, 23, 19, 76. Yikes. Okay, there you go. Okay, so here's the BST. It looks kind of like shit, but it's okay. Just for demonstrational purposes. So when you go about doing this traversal, remember on like the slides, like for each traversal, you had something like left, right, root, or like root, left, right, or something like that. Okay, so I want you guys to think of it like this. So for pre-order, that checklist is root, left, right, if I'm not mistaken. So here's the easy way to traverse through the tree, given only that like ordering of root, left, and right. So what I'm gonna do is I'm gonna, for each node, make like a little checklist of that exact order. So RO is gonna denote root, L is gonna denote left, and R is gonna denote right. And I'm just gonna create that for like all of these nodes here. I'm not gonna do it for all of them actually, but get the idea. So when you're doing this, each node will have this kind of checklist. And again, since we're doing like a search or we're doing like a traversal through a binary tree, we can only look at one node at a time. So let's just like draw a red circle to denote the current node that we're looking at. And it should be obvious, but we're gonna start at the root. So here's what you wanna do. In the node that is circled, or in the current node that you're looking at, look at the checklist, and then from left to right, check off the things. So when you check off root, that indicates that if you're keeping like a master list or something, 50 is going to be printed. So let's just say we have like this output log up here where we print out 50. That is exactly what happens when you cross out root. And then, okay, we crossed out root. We go into the next thing in the checklist, left. Okay, so that's the next thing we should do. Cross that out. When you cross out left, what you do is you take the circle or the node that you're looking at and you shift that to exactly where the left node is and do nothing else. You don't print anything. You don't add anything to the list. You just go directly to where it's going, right? And then literally, if you just recursively follow that, that'll exactly get you the traversal, right? So now that we're in 17, this is the node we circled and we're looking at. We look at its checklist. Okay, looks like we have to cross out the root, which means that 17 is printed. So we add 17 to the list. Okay, that's done. We look at the next thing in the checklist, cross out left. That means all we do is just move left right here. Okay, now we're at 9. Cross out root, which means we add 9 to the overall like master print list. And we go left. And here's the case where we can't go left. So if we can't go left, we do nothing. So we're done with that step. And then we can just go ahead and move on to this R, which means we move right. Okay. So we move right, left, right, root. I don't know. Oh, wait, no, sorry. It is root, left, right. Same thing. Cross out root. That's the first thing in the checklist. So 14. Cross that out. What's the next step? Left. Okay, so we move left. We move left, and we're at 12. Cross out root. That means we print out 12, as so. And then there's no left node, so we're done with that. And there's no right node, and we're done with that. And then at this point, when you finish everything in a checklist, all you got to do is just move up to the parent node or where it came from, and then you just continue checking off the checklist as usual. And in this case, oh, I should have checked out left. Since the only thing left to check out is right, and there is no right node, we checked everything off there. Again, we recursively move up to where we came from. Looks like 9 is already checked out, so we move back up. And then we're at 17. And then we just follow the checklist as usual. And because right's not checked, we're going to check that off, move right, and then follow the steps there. I'm not going to do the whole thing, but I hope that makes sense. It's just that process of having a checklist for each node and then kind of like recursively following the steps, traversing through the tree. And no matter what you have for any of the traversals, like the in order, pre-order, post order, or whatever, as long as you have that three like operation order code down, as long as you write that for each node and follow the steps in that exact manner, you should be able to find the traversal exactly. So it should just be this middle one right here. All right, so this is relating to stacks and queues stuff. Um, if you think of a stack, it follows the last in, first out principle. Here, I'll draw a picture, I guess. So last in, first out means that, okay, say we're adding stuff to a stack. Here's 1, here's 2, here's 3. If we want to remove something or we want to pop something, which is called in a stack, you remove the thing that was most recently added, right? Because last in, first out. So if we were to pop, you just do it like that, right? And then for a queue, I don't know, you might want to like draw it out like this. So say this is like, I don't know, say this is like a line of people and this is the Apple store over here. A queue is just like intuitively like a line of people. If someone joins the line, they're going to join in through here. And if someone wants to leave the line, the person that was there first leaves, right? So it's basically, that's the gist of it. Shouldn't be too bad. And yeah. And if you think about it, dirty plates will follow that stack data structure. Should be kind of obvious from like the picture I drew. But if you have like a stack of dirty plates, you're not going to take one from the bottom and like wash that one because it was in the stack first, right? You're just going to take whatever's at the top and wash it. So again, that's going to follow that stack paradigm where whatever was in last, you're going to clean first. And in programming or Java terms, that's just directly going to be function calls for recursive method. Because again, when you're doing recursive calls, it's being put on the call stack. And as we know, like function calls, they're being kept track of with a stack data structure. So yeah, those two are going to be the ones that are correct. I'm going to do one last one if you guys don't mind. I don't think I'll be able to get to the last 6 because we seem to be out of time, but these will be posted on Canvas. So you can look at them yourself. Whoever wins this question will win the $10 Target gift card. Let's end strong here. All right. Nathaniel S. Come up here and receive your prize, dude. Could we get a round of applause for our winner? Very, very nice. Where did it go?
I think you threw it earlier.
Did I throw it?
Or like it.
No, I picked it up at one point.
Oh, you did?
I think so.